what is the profiler? So the profiler, in general, for our non-developers, that is to say, the people who aren't actually building the APL system, this profiling tool is of less interest in its detail, and its primary interest is it gives you, the end users, an opportunity to um, profile your specific application code and send to us a abstract of that that lets us explore the performance details of it. So I'll try to show you how that is. It's completely anonymized. There's no data, actual data that gets recorded by the profiler. What it does is it looks at argument types and ranks and gathers this information into a format that can be saved and then transmitted to us. But this will make a little bit more sense as I demonstrate this. But the first thing to know about the profiler is there is a command profile you can type, or it's usable as a quad function or as a system command. I tend to use it as a system command instead because I can abbreviate it to just PRO rather than typing out quad profile. But if you type in a question mark here, or if you want to use the quad function, you can say and give it this argument, or you can say help. It will display this little summary of the profile information, and this is just a quick reminder of the different commands. So I'm going to go through a couple of those commands, and then we'll come back around and look at them in a little more detail. But the ones of particular importance are the on command and the off command. This turns the collection of profile information on and off. And if you're going to be profiling, you want to turn that on. The other one to know that works in conjunction with this is the clear command. Because if, for example, you turned the profiling on, you ran for a little while, then you turned it off, and then you turned it back on again and ran some more, you would be accumulating more profile data on top of the ones that you had previously created during the previous collection session. That is, between the time you executed the on and the off. And then when you execute on again, you'll now be collecting profile information again. The clear command is used to clear the accumulation buffers. And then there is a command to display the information. And for your purposes, you might be interested in displaying this information for your own interest, but as far as, and it could be potentially useful to you to understand where execution time is being spent in your application. Maybe I'll try to make this a little less abstract here, and I'll show it, but let me just finish rounding this out. There's also a save command, and the save command takes the collected information and stores it into a file on your system, so either into a JSON or an XML file. JSON by default, and that's a more compact representation of the data. So it saves that, and then you can then later reload that same data, or if you're interested in demonstrating to us where you have hotspots or especially slow performance in your application, we can use the profile data to allow us to introspect where the bottlenecks are occurring in your code. So let me try to make this a little less abstract. I'm going to make a simple function here, and I'm just going to make this function named foo. And that function is going to simply say x is equal to 10, and then it's going to say y is equal to x plus x minus 5. Let's just say very, very simple function here. So obviously,
excuse me, Pat, can you increase the font? Someone had requested that.
Sure.
Please. Thank you.
You see that a little bit better? Is that sufficient for?
I think so. Thanks.
Okay. All right. Yeah, thanks. That's a good idea.
I like you.
All right.
So, on the bottom.
Let's take a look at our function here again. So this very simple function just assigns a value to x, and then so now if we execute this, obviously it doesn't really display anything, but if we want to profile that, we would say, now you can use the quad profile. I tend to use the command. So profile on. This was off and now it is in the on condition. Now if I run this function, and then I can turn this off, or I can just query it. So let's just take and let's look at what we've collected here. So what it's showing, now this is not a very good example, I will say this, because it doesn't iterate, it doesn't actually run, it's a very short, quick running code, and sample size being small, you're gonna have rounding errors in your collection, and so it's not gonna give you a particularly good assessment of where your time is really spent. I'll show you a little bit more a bigger example here where we will set up a for loop and it'll run through a few thousand iterations, and we'll take a look at that. All right, so what is this showing? In the standard view, it's showing you what are called the X codes. The X codes are basically internally, when you run an APL program on our system, it compiles the APL statements into an intermediate code, into executable code called Xcode. So we compile the statements as they're executed the first time, and then and then subsequent to that, we um, uh, execute that Xcode program. And actually, let me show you this, because this will, and I hope this, I'm not beating around in circles too much here. There is, just as you know, we can say quad VR function. There's another function called quad IR, which is called internal representation. And what this is going to show us is the internal representation of the function as along with the X codes that are executed. And so if you do the quad IR, you'll be able to see on a statement by statement basis for any statements that have been executed. For statements in a function that didn't execute, like if they were skipped because of a conditions or branch statements or unexecuted clauses of if then else statements, then in those cases, those statements won't be compiled. But any statement that has been compiled or that has executed will be compiled. So let me just show you real quickly what this does. The first statement in the code says X is assigned 10. Internally, the way it's actually implemented is there is an execution code called XFC, which is to fetch a constant value. So we've pre-stored this value. It stores it and it pushes it onto what's called the value stack. And then there's an X code for assigning it, and it assigns it to a variable. And then there is an X code which marks the end of the statement. And there's a variant of this which displays, and one that is non-displaying as a function of the last operation that was done on the line. So if an operation does an assignment, it does a non-display. It has a no display potential in that case, and so it doesn't display that. But if I just computed 10 plus 10, it's going to by default display the result value 20. And in that case, there would be an XEOSD on the end of the line, and that is there to take the last value that was computed and display that. That's where your output gets generated. But in the case of an assignment, we eat the output, or I mean, we take the value and we just discard it and we don't display it. The next one is in a similar fashion. It starts on the right hand end. It fetches the value 5 over here. It then fetches the X value, and then it applies the minus primitive to it. So it computes this part of the expression, and then it fetches the value X, which is this left argument here. It applies the plus primitive, and it assigns the result to Y. So those are the operations that happened, and we just went through them the one time. But if we display these in the profiler, okay, if we display these in the profile. Now, one thing I kind of did is skewed my data a little bit because I used this quad IR function and I didn't turn off my profile. Let me do this. Let me say profile clear, And our profiling is still on. I didn't turn it off, so we can run the function again. We will run that function, and now we'll display the the output for this. So what this actually tells us is, in this particular thing, which didn't do very much work, most of our time was actually spent actually compiling the codes the very first time they were executed. If I were to execute and capture this again after I've executed actually what we're actually seeing also is the compiling of this immediate execution expression, that then the code of the foo function is executed, not the individual statements, because there's statements in the foo function get done. So now you can see here, one of the X codes is the applied dyadic scalar primitive. And you can actually see that there are two variants of this. There's one which is applying the minus function, and another one applying the plus function. What you can also see is there's one instance of doing a assignment to a variable. This is the assign user variable. There's also a case of invoking one niladic function. That's because we typed foo on the line here. We had to execute the foo function to get in here. And this is what I'm going to show you in a minute, is where you might find using the quad profile to avoid some of the other overhead can be used, because you can embed the profile on and off inside of some function context. And if you want to sample a particular place, say above and below the bounds of some loop, if you want to focus on a very specific area where you're having a bottleneck in performance, it can be useful to profile just the section of code that you know is a hotspot, and in order to try to help tune performance. And I just want to say, this is an iterative process as far as our company and you, the user, is concerned, in that if you find performance bottlenecks, we're interested in knowing about that. That's one of the reasons we built this tool, is so that in the field, using your application without us having to run your application, we can collect information about how your some of the specifics about where your application is spending its time. What is it doing? And therefore we can say, oh, well, if we could make that thing faster, we could improve the performance of your overall application. And in some cases, we can help to guide you with that, or to guide you with some suggestions, and or it points out to us places where we could potentially optimize the system, spend more effort to optimize a system in a particular case. Okay, so I'm going to go on to a little bit another function. So I'm going to take the profile off and profile clear, and then I'm going to load. Let me see. Is this the one that I want? Yeah. Okay. So this is a little bit of a more complicated function, and what this one ends up doing is it's doing some timing in it, but inside of it, there's a for loop that runs for the number of iterations you specify as the argument. And it goes around here and it does a kind of a silly calculation. It's not doing anything constructive here. It's basically doing a catenation into a vector, and in a vector that you're building one by catenating one element at a time over and over in this loop. Not an efficient thing to do, generally speaking. But I'll talk a little bit about that. Then it just does a little bit of simple math, and then does an outer product. And the whole point here is to just spin and spend a little bit of time running. So if I run this function, 10,000 iterations, it comes back. Well, let's put profiling on. Let's put profiling on, run this, 10,000 iterations. Now, I recommend, if you're doing profiling, if you're exploring something, you get accustomed to using profile on, run the test you want to run, turn profile off. Don't leave it on, because if you don't turn, I have found when I'm using this, if I don't remember to turn the profiling off, then other explorations I do will continue to accumulate profiling data, which can be confusing and skew our results. So I turn the profiling off, and now I've got a sample. I can turn it back on and accumulate more into the same profiling sample, but this is useful for me as a way of doing this. So now I'm going to do profile, and I'm going to do, well, actually, first thing I'm going to do is I'm going to just as a simple test, I'm going to say profile save, and I'm going to say I'm going to save this profile for here as a file into my directory. So it is saved this file. By default, it becomes a .json file. So I've saved that, and if I look here, so let me take and look at. So I've cleared the profile, and if I say profile get, I don't have anything. There have been the 0 iterations, number of statements that are primitives that have executed, Xcodes really, and 0 milliseconds were spent doing it. So there's nothing accumulated here. But if I come up here, if I load, I can reload that profile. And if I display it now, I've got that profile information. Now, this is the way that we would tend to use it if you want to interact with us and send us your profiling information. Is you would collect your profile data, and then you would save it into a file, and then you could zip that file up, or generally you don't need to worry too much about zipping it, most likely, because it's not going to be really big. And so this is the way that you would go about saving the profile. And then when we get that file from you, we would load the profile and be able to assess it. Now I want to show you a couple of ways that this can assess the data. The first way is the default way, which is if I just say get the profile, it's going to return the profile information to me in a default format, and that default format sorts the X codes that executed. So you can see these different X codes here that were executed, and they're sorted by the one that's the most expensive first, and down to the least expensive um, one. And then within that, it shows us a breakdown in those cases where there is a subcategorization. So in here, we had a um, we had a couple of different primitives. So this is the apply dyadic scalar primitive, XASPD internally. And we did it for addition, multiplication, subtraction, and division. And so we can look at that. And then we also had an outer product. This is the XJDPFN. This is the outer product one, and we see that we had one kind of outer product, jot dot plus. If I had done a jot dot times in here, that would create another entry in here. Also, take a note, under some of these primitives like this, like the plus, we can see a couple of variants of it. We can see that we had an integer matrix plus an integer matrix in one case, and over here we had a Boolean scalar and an integer a scalar that were added together. And so similarly, you can see that we have a couple of different variants of these, and this is useful for us because we can see how those things are attributed there. We also can see a bunch of variables that got fetched. Now these are going to be um, one variable to the next in general won't matter that much. They're going to all be about the same speed, taking into account the fact that statistical variation will occur. So you may find some differences here, but these are very different in their scale, in their magnitude, because in one case the variable n got referenced 20,001 times, and variable x got referenced 20,000 times, and so forth. And the t and the u only got accessed once. And similarly with assignments, you can see this. And you'll also see that we had a for loop, and it in that statement at the end of the for loop executed 100,000 times. We did 100,000 iterations. That kind of makes sense. And we could see how much time got attributed there. And for all these other things, here's another a monadic non-scalar primitive, which is iota, gets attributed here. Now, this is useful information to us, potentially useful information to us, but we also can display this in a couple of different ways. So that was just the standard presentation of the data. If I say profile get and I give a different format, I can put it in what's called ops format. Now, ops format is going to sort, it's going to have the exact same data, but it's going to sort it in a different fashion. So what it ends up doing is it shows us each of the different ops that have been done. So the most expensive was the catenation operation. And of course, you might imagine this because it's a progressive catenation that we're doing. In our code here, in our function, we had this statement here, s comma is assigned value. This is the same as if I had written s is assigned s comma like this, but in APL plus win, this is a performance optimized operation. It turns out I'm in the midst of optimizing this in APL 64, because in APL 64, this statement has performance exactly equal to this, which doesn't have the special optimization in it. But and I was hoping to have that able to show you guys today, but I don't have that work done. But this will soon run much, much faster. So this is a construct, which is it's a really nasty construct in APL. If you're building output, for example, by piecemeal catenating together a bunch of pieces of the text, this progressive catenation, every time you concatenate more data to it, you are having to take the entire previous result and copy that over into a new memory slot and add the new data. So you keep copying ever increasingly bigger swaths of data, and it's what's called an n-squared algorithm, which means it as the size increases, the time that it takes increases proportional to this, roughly speaking, to the square of the size, rather than linear, which would be more preferable. And the algorithm that I'm building allows this kind of catenation to work in a more linear, roughly more linear fashion, so that the copies, there's not nearly as many copies. So, but the point of it is, in the present system, this Xcode, which is specialized for doing this particular operation, called catenate into, really, is doesn't have the optimizations that it has in APL plus Win at the present time. It will be in the next release, this in speed up, but it's the most expensive thing. We've done 10,000 iterations, and it's accounting for 17 milliseconds of our time. If I were to do this 10 times more iterations, we would have substantially more than 10 times the time that it would take. The number of milliseconds it would take would be substantially more than 10 times what we see. But that shows up first. This sorts this way. So by using the ops, you can look at the various specific ops that were done, and see this. But what you'll see is that in the other one, it broke out for specific, how much did I spend doing particular, well, I have an integer matrix plus an integer matrix was taking a certain amount of my execution time. And so I'm that all information about the data types is omitted here. So you can see this is just sorting on the operations without those details. There is another form that I can use here, which instead of ops, I can say args. Again, these hints for these types are summarized in the profile help. So if I said write paren pro and then question mark for the help information, that would display to me that little profile output that I did at the very beginning of the session. So if I sort by args, what this is going to do is it's similar to sorting it by the ops that were done, except within that you will see the specific operations that are done along with their argument signatures. Now, the argument signatures that we're collecting at the present time just characterize the data type and the rank of the array, and the things that are said here would be things like int or double for the or bool for the boolean or integer or double data types, and then the suffix on it is going to say scalar, vector, or matrix. And if it is a higher rank, it will say that rank of the array, like rank 3 or rank 7. So the basically the type and rank of the arrays are given, but there's no hint about size. And so one of the enhancements that might come in the future, although we haven't had demonstrated necessarily a need for that to come up, but that would be to further subcategorize for a particular argument signature, is to look at the number of elements that are being operated on and have some set of categories within that. So we might have subcategories under a particular combination of arguments to categorize how big those arguments are. So that can be useful in understanding the where our time is going. But at the present time, we collect all this information, and then we have several ways of displaying it. So like I said, for the sake of your curiosity, you might decide to use the get args, get ops, or just the get. There's also a form called get codes that I didn't show you. This one just shows us the X codes without any information about the specific ops. So for example, the XASPD is apply dyadic scalar primitive, and this is being used actually to do plus, minus, multiply, and divide in our code, but it's all done under the cover of this Xcode operation, and the subvariant of it to do which specific primitive is hidden from us when we display codes. But sometimes slicing the data this way can be useful to understand where your time is being spent. And I do emphasize, and I'm beating a dead horse here, is to set expectations. For the most part, for end users, the profile tool is your most likely scenario is going to be to find a hotspot in your code, and this may be overall. Let's say that you have a particular big calculation that seems to be taking longer than you'd like it to take. Well, you can set that up and you can collect profiling information around that hotspot. So let's take our foo function here and let's exclude. So let's go in here and we're going to say profile clear, and then we're going to say we're going to turn profiling on at this point, and here we're going to do profile off. So what I've done by virtue of this, is I've set this up to collect. And by the way, this code might be optional. You might not clear it because you might want to have multiple places in your code where you specifically focus, where you know you have a bottleneck. Maybe you've used quad MF to monitor where the time is being spent in your application. You can see that roughly, but it might be, well, I don't know why this is running so slow, or this seems inordinately slow. You could collect that sample, but you may not want to clear it because you may want to have several different spots that you collect data in. But I'm clearing the data, then I'm turning profiling on, and then I'm turning it off. And what that means is this code here isn't going to be profiled, and the code that's above here will not be profiled, nor will the invocation of foo from the command line when I execute that. So all of that stuff's going to be excluding from the profile, and all we're going to be looking at is the bounds of the for loop. So we will see the code that's in the for loop, and other stuff will be omitted from that. So let me save that function, and then I'm going to run foo again. So oops, I didn't use the argument, sorry. So we run this, Now, the quad profile function does kick out a little bit of output. You can sync that output if you want, if that's important to you. But anyway, this data is there now. Now, if I say profile um, get, we still have a bit of data, but some of the stuff that is going to be missing from the data is some of the other invocations. There's no longer, well, it was in the other thing that there was a function called XAUM. That was actually when we were invoking the foo function from immediate execution. Well, we're no longer doing that within our profiling context. And so there won't be an XAUM in here. We're not going to see that overhead. We're going to just see the overhead that's pertaining to our specific function. So we also, because of um, uh, we did there was a division that was done, and this was for computing the time that was spent when we were collecting the elapsed time for our application with that code, with this foo function. We had at the bottom down here, we're using quad TT and quad TF to get high resolution timing for it. And by that division here is outside of the bounds of the profiling. So you could see that is also the references to the quad TT. So there's no longer any references in here to quad functions. There were up in here, there would have been this is a niladic quad function. XQD1 is niladic quad function that was being referenced, and that was in fact referencing the quad TT or the quad TF functions. But those are outside of our profiled sample area, and therefore we don't see those. So this is a way, and in some instances, you're going to want to set the profiling up before you start your thing. That is to say, let's say you'll X load a workspace, you'll put profiling on, and then you'll execute your latent expression if you have an auto start on the workspace. Let it run up to some point, possibly to a point of completion, and then grab your sample. And your sample is, again, if you're going to send it to us, it's going to be done by saying profile save, and then I'm going to save it. Now, there's no safety in the saving, in that if you say save pro and then I say it again, I'm going to save. It's not like a workspace when there was a WSID and you can't, if it already exists, I can't save a new name on top of it. If I say a name in the save command, it's going to overwrite what was there previously. So there's no uh, concept similar to the safety that workspaces offer, with not overriding workspaces that have a different name that were already in existence. So therefore, be careful with that when you save it. But this is what you would often do. You might examine your profile data using these various tools, but you're going to, my suspicion is that outside of just curiosity, um, these samples that you collect may not be real useful to you in tuning up the performance of your application. With some experience, they might be, and with a little guidance, they might be, and so that's useful potentially. You can correlate it, as I said, also by using the quad IR function to to show you what the X codes are for each particular line that got executed, what actually, what are at the low level primitives, what was executed here. And if you've got a section of code that's really slow, you can look at that, and then in combination with profile, it might help you understand what's being displayed in the profiling output. But for the most part, the profiles are going to be useful for us to be able to look at hotspots that you point out in your application, where you, and in particular, if you're migrating from APL plus Win to APL 64, and you have a particular place that that is problematic, is a bottleneck for you, by using the profiling tool, you give us insights into specifically where the bulk of the time is being spent in your application, which may turn out to be, I can't make promises here in a generic fashion, but we're motivated by trying to make things run faster. So if you provide data to us, it gives us a better opportunity to understand where we can, where it makes sense to put the effort to try to make things run faster. So um, that's it. So with that, I'm pretty much showing you um, what I
Pat, I
have
think
to.
it's time
Yep,
for questions.
questions.
This is
That's what I'm
great.
thinking. Yep.
That's good. So this is Joe Blaze. This is an opportunity for you to provide us with information that can help you, and because we've been using this on some apps that we have more familiarity with, just as Patrick said, that the cat into operation. When we find that, we examine the code and see if using some of the new features we have in .NET, or if applying some other the programming tricks that we might have, we can improve the operation. So this is a good opportunity. You have applications. You can use this if you need assistance with that. You can send emails to support at APL 2000 if you run into, how do I use this in my own case or whatever. But we're looking for this kind of input. It will help you to improve your app uh, if we get this. So let's hold off for a second on our talking, and we'll take the questions on this or any other topic.